Yo, what's good everyone? Today we're going to be talking about the P-adic valuation. It's just a method to denote the exponent of a prime number in the prime factorization of some integer. As you can see on the screen right here, it's denoted Vp of n, where p is the prime number and n is the integer that we're trying to find the P-adic valuation of. And since it's just a method to define something, it's not going to be very complicated just by itself. That's why we're going to be introducing some theorems, lemmas, and first some simple propositions that will heavily use this notation and introduce some properties of the P-adic valuation. So make sure to familiarize yourself with this notation before moving on. Alright, so now we're going to prove a simple proposition, which is Vp of AB is equal to Vp of A plus Vp of B. And so if you're trying to prove this yourself, feel free to pause the video, but just remember to use the simple definition of the P-adic valuation. There's not going to be anything too complicated going on in this proof. So the proof is as follows. By the definition of the P-adic valuation, p to the power of Vp of A divides A, and p to the power of Vp of B divides B. This is because, again, Vp of A is just the largest exponent of p in A. So that's why we can say that p to the power of Vp of A divides A. And in fact, it is the largest power of p that divides A. And so now we can write A in terms of p to the power of Vp of A, and similar thing going on for B. So if we write A is equal to p to the power of Vp of A, that's not enough, but it is necessary because p to the power of Vp of A divides A. To make it sufficient, we can just multiply by some m and assume that p does not divide m. We can do this because since Vp of A is the largest power of p dividing A, m must have 0 as its power of p. So p does not divide m. And for b, we can just write b equals to p to the power of Vp of b, and then times n, where again, p does not divide n. Guaranteed. And so, since we want this expression for a times b, we should just multiply these two equations together, right? So that the left-hand side becomes ab, and the right-hand side becomes p to the power of Vp of a plus Vp of b, and then just times m n. And since p does not divide either of m nor n, we can safely say that p does not divide m times n. And so now we just take the P-adic valuation on both sides. So it becomes Vp of AB, and then the right-hand side is just Vp of p to the power of Vp of A plus Vp of B, and then times m n. And then again, since p does not divide n times n, this part over here does not contribute anything to the power of p in this expression over here. So therefore, we can just remove it completely because it doesn't contribute anything. So all we're looking at is p to the power of Vp of A plus Vp of B. And this is obviously, this whole expression over here is obviously just Vp of A plus Vp of B, because the largest exponent of a prime that divides a prime to the power of some exponent is just that exponent. And again, the left-hand side is Vp of AB. And so we're done. The second proposition that we're going to be looking at right now is Vp of GCD of A1, A2, dot, dot, all the way to AN is equal to the minimum value across all the VPs of A1, A2, all the way to AN. So this is just left as an exercise for whoever's watching this, but I'm just going to give one simple example that's probably going to come up in actual problems with GCDs, except we're going to be translating this into P-adic valuation language. So just to demonstrate this, let's say V5 of GCD of 50, 125. And what we would usually do for this is just compute the GCD of these two, right? And so we would prime factorize 50, which is just 2 times 5 squared, and 125 is just 5 cubed. And so clearly the GCD is just 5 squared. So this is just equal to V5 of 25, and this is just 2 by definition. However, according to this formula over here, you can write min V5 of 50, comma B5 of 125. And so this becomes the minimum value across 2 and 3, because even though 5 appears 2 times in 50, and even though the power of 5 isn't the only thing that's part of the prime factorization of 50, we can just take that part and we don't have to look at the other divisors. And so this is just the minimum value of 2 and 3, and so just 2 again. And so this is just a very simple example, and I hope this gives you some intuition for the proof. So let's move on to the third proposition. So this proposition is very similar to the previous one. It's just the same exact thing, except you're using the least common multiple. And so let's just write it out. Except we're using the LCM, and the right-hand side is the maximum value across all the BPs. Alright, our final proposition is BP of A plus B is greater than or equal to the minimum value across BP of A and BP of B. So now we're going to be talking about a lemma that's really useful to both the Amy and the Olympiads. It's called the lifting the exponent lemma, and it basically states that if you have an odd prime, P is greater than 2, and GCD of P and AB is equal to 1, which means that P is relatively prime to both A and B. And the third condition is P divides A minus B. Then we have the equation VP of A to the N minus B to the N is equal to VP of N plus VP of A minus B. And when I first learned this lemma, I thought, hey, this term is greater than 0 just because P divides A minus B, so that's pretty interesting. And you may be wondering, is there an LTE for even primes, namely just 2? Well, there is another version of this lemma. So the version for the prime number 2 is as follows. If we have odd integers A and B, and a even integer n, then the following equation is true. V2 of A to the power of n minus B to the power of n is equal to V2 of n, just like the previous one, except we have the second term being V2 of A squared minus B squared all over 2. And so this is the second version of the lifting the exponent lemma, and it's still pretty interesting, but it's just a tiny bit harder to remember, so make sure that you take your time. Okay, so the Amy problem we're going to be taking a look at is the 2020 Amy 1 problem 12. And if you read this problem, you can see that it basically begs us to use LTE because it involves A to the power of n minus B to the power of n, as well as odd primes. So we know we're going to be using the first version of LTE. And since we're using that version, we know that P must divide A minus B in order for it to work. And therefore, 149 minus 2 being computed would be really helpful. And so that's equal to 147, which is just 3 times 7 squared. That means that we can use LTE on the prime number 3 for this expression over here, and also the prime number 7. And for 5, we're going to deal with that later. And so looking at P equals 3 and 7 first, if we have V3 of 149 to the power of n minus 2 to the power of n, we know that's equal to 3 because in the problem statement, it's 3 to the power of 3. And so using LTE on the left-hand side, we get V3 of n plus V3 of 147, and the exponent of that is just 1. So it's just 1 is equal to 3. And so this just becomes V3 of n is equal to 2. And we can do the same exact thing for V7 of this expression over here. And if we just do the same exact thing as what we just did, we can get V7 of n is equal to 5. And so far we know that the prime factorization of n definitely includes 3 squared and 7 to the power of 5. And so now we just need to deal with the 5 as the prime number. And so it turns out that if we set n equal to 4c, we have 149 to the power of 4 is congruent to 2 to the power of 4, mod 5. And this is useful because we want this to be true. We want the two terms subtracting each other to be divisible by 5, because this is just the same thing as 149 to the power of 4 minus 2 to the power of 4 is congruent to 0 mod 5. So now that if we use this substitution, n is equal to 4c, we can directly apply LTE. And so we get V5 of 149 to the power of 4c minus 2 to the power of 4c is equal to 5, which is from the problem statement. And so the left-hand side becomes V5 of c plus V5 of 149 to the power of 4 minus 2 to the power of 4. And note that we're not doing V5 of 4c and then 149 minus 2, for example, because we want to make it c, and we want this to be divisible by 5. And so it's equal to 5. And now we just need to find the power of 5 in this expression over here. Well, if we just do a simple check, mod 25, this is not congruent to 0. So therefore, the largest power of 5 that divides this is just 1, because we know that this is indeed congruent to 0 mod 5. So that means V5 of c is just equal to 4. And so we have c 5 to the power of 4 does divide c. And so since n is equal to 4c, we know that 4 times 5 to the power of 4 must divide n. And so going back to what we got from 3 and 7, we know that this divides n. And now we know that this divides n. So the final prime factorization is 2 squared times 3 squared times 5 to the power of 4 times 7 to the power of 5. And that means the number of divisors is just 2 plus 1 times 2 plus 1 times 4 plus 1 times 5 plus 1. And this is equal to 270, which is the correct answer. And I hope this Amy problem was really fun for whoever's watching this video, and I hope you learned something from this video. Thank you for watching, and stay tuned.